Hello Internet, welcome to Phase Theory, the show where science and the pain of reading graphs come together, along with countless hours of big braining efforts and animating in PowerPoint for over 72 hours. Please God help me. On today's episode of Mind-Bending Pain, we're going to be talking about binary eutectic systems. To understand this mindfuck, I'll let Bafemos recap on the basics of a phase diagram.
Hi, welcome to F***ing. Let's first understand what this actually means. A binary eutectic system refers to an alloy structure and how it can change with time and temperature. We can represent this with phase diagrams, which shows us where and how phases would change. Think of an alloy like steel. We know that when steel is blasted with heat, its properties change. This is because there is a change in phases in the structure. The easiest way to figure out the temperatures and compositions that we need is to look at a phase diagram. Let's look at a simple binary diagram, which is also referred to as a binary isomorphous system. Binary in this case actually means the presence of two metals or elements in the mixture, just like how copper and zinc can form brass. Let's use a copper-nickel diagram as an example. Like I said before, at different compositions, a lot of things can happen. Depending on the temperature and amount of each component in the alloy, the phases differ. For example, let's take a look at a composition of 60% nickel, right here. At a temperature of 1200 C or 1200 degrees Celsius, the alloy is still in its solid phase, represented by alpha. If we raise the temperature to 1400 C or 1400 degrees Celsius, it changes to a liquid phase represented by L. But there's still this weird oval-shaped part of the diagram. This represents another phase, which is a phase that consists of both solid and liquid phases. Let's call it the mixture phase so that we don't confuse ourselves. This is represented by alpha plus L. The boundaries of the oval, which separates the three phases, are represented as the solidus and the liquidus line. Now let's look back to the rest of the phrase, the eutectic part. Eutectic is actually a Greek word, meaning to melt easily. So we can infer that this word has something to do with the melting point. So eutectic in this case has something to do with the phases that are present and how they interact with each other. Let's take a look at a copper-silver diagram to understand better. At a glance, we can tell that this graph shows a lot more than the copper-nickel diagram that we showed earlier. These diagrams differ based on the These diagrams differ based on the alloys and the type of metals or elements that are present in the composition. Let's look at the similarities first. There's still the same components of alpha, liquid, and mixture phases. But now there's also a beta right here at the solid part. This actually represents another solid phase that can be formed, along with the mixture of alpha plus beta. So we can see that there are three solid phases compared to the one solid phase that we saw in the previous diagram just now. The addition of beta also changes the mixture phases. There are now two phases, alpha plus L and beta plus L. This new beta represents the phases that have a higher composition of silver than copper, whereas alpha represents the phases that have a higher composition of copper than silver. The only thing that doesn't change here is that there is still only one liquid phase, along with the solidus and liquidus line. But there are also additional lines right here and here. The lines at the side here are what separates the three solid phases, known as the solvers line. There's also this horizontal line right here with a weird dip that sorts of separates the solid and liquid phases. This dip is called the eutectic point, which is the lowest temperature at which the liquid phase starts to form. That horizontal line is called the eutectic isotherm, which helps us visualize the point easier. There's still a lot more data that can be learned and calculated from this graph. I'll bring it back to Kelvin to explain them.
Now that we know how to read the diagram, Now that we know how to read the diagram, let's move on to some applications. Let's take a copper-silver alloy in the liquid phase at a very special composition, the eutectic composition, and let's cool it until it solidifies. We see that its microstructure forms this zebra-like thing. We call this sort of microstructure the lamellar structure. But hold on a minute. In the lamellar structure, we see two solid phases. But how did one liquid turn into two solids? Let's rewind a little. Right here. At this point, where the liquid starts to solidify, the system undergoes a very special reaction, the eutectic transition reaction. Let's break down this equation a little bit to understand what's going on. Finger. From the reaction, we see that a liquid at the special eutectic composition is being cooled to form two different solid phases, alpha and beta, with their own unique compositions. So we see from the eutectic reaction that as the liquid cools, it transforms into two solid phases. Alright, cool. We now know that a liquid of a binary eutectic system solidifies into two different solid phases. But this doesn't explain why the zebra-ish microstructure forms. To answer that we'll have to turn to atomic diffusion. There are two key concepts we must first understand. 1. From Fick's first law, we know that diffusion happens in response to a concentration gradient, kind of like how perfume sprayed at one end of the room spreads around the room. The second concept is something known in classical physics as the principle of least action. When you go to the supermarket, you would most likely take the shortest path to it rather than going one big roundabout before reaching your destination. Similarly, natural systems tend to go down the path of least resistance, and such is the principle of least action. With these out of the way, we are now ready to tackle this problem. Let's go back to the lamellar structure real quick. Now let's zoom in on the microstructure. Here, we see that the alpha phase has significantly more copper atoms than silver. Conversely, the beta phase has significantly more silver atoms than copper. So we see that between the alpha and beta phase, a concentration gradient will be established and the diffusion of copper and silver atoms across the phase boundaries will take place. From the principle of least action, we know that the microstructure that forms must allow for atomic diffusion to take place with the least amount of energy required. For the easiest path for diffusion to take place, the alpha and beta phases must be next to each other so as to minimize the distance that the atoms must diffuse across and to minimize the energy spent for the atoms to break bonds and squeeze past their neighbors. This is why the alternating alpha-beta microstructure, otherwise known as the lamellar structure, forms. Let's do a final recap to check what we have learned. We learned the main differences between a binary isomorphous and a binary eutectic phase diagram and how it affects the phases formed. We then talked about the structure that a binary eutectic alloy forms when it is cooled, the lamellar structure. And finally, we talked about the corresponding transition reaction that causes the lamellar structure to form, along with why it's formed. But hey, that's just a theory, a phase theory. Thanks for watching.